Hello and welcome to part 2 of the section 8.2 notes. In this video we're going to go through this page 56 where we learn how to find the sum of a geometric series. So this is our first big sort of result about infinite series. Let's first start with a sequence. Let's suppose it's called an. We're starting with n equals 1 and going up to infinity. Then remember, in the last video we talked about how you can form a new sequence of partial sums, right? So this, if it helps, you can think about this notation here as just being where you start with the first entry and you keep adding, so we'll go A2 until you get to that nth entry, right? That's what this means, right? All right, and now this is a new sequence, right? So S1 always equals A1, S2 will be A1 plus A2, S3 is A1 plus A2 plus A3, and so on and so forth. Okay, now if that sequence of partial sums converges, just like I said in the last video, then that's what we define the sum of the infinite series to be. Okay, so the sum of an infinite series is not directly related to the sequence that you're adding up, right? There's a sort of an intermediate step here where you have to define a new sequence of partial sums. I know I'm starting to sound like a broken record, but students, especially if you're first learning this, often get a sequence and its corresponding infinite series confused. So again, if the sequence of partial sums converges, then we say the infinite series converges, and likewise, if the sequence of partial sums diverges, we say that the infinite series also diverges. All right, so let's look at a geometric series. So we saw this last time with like the 1/2 plus 1/4 plus 1/8. But this is essentially the general form. Notice you have a constant, and then what's called a common ratio, or just a ratio for short, r, that gets keep getting raised to higher and higher powers. And so this is the notation to summarize that. So this is the sum n equals 1 to infinity, a times r to the n minus 1. And notice that the r is the only thing affected by the power. This a is sort of persistent always to the first, right? So you always have just a normal a here. All right, so let's look at the partial sums here. When n equals 1, I get a times r to the 0, which is just a. The second partial sum will be a times r to the 0 plus a times r to the, now plug in n equals 2, you get a times r to the first, right? So these two added together is S2. These three added together is S3, and so on and so forth. So you notice that Sn is a plus dot 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 a times r to the n minus 1, right? It seems like the power of r is trailing behind the index of the partial sum by 1, correct? The first 5 added together, these 5 right here, form S5, and so forth. Okay, so now let's suppose that all of the r value, or the r value, is just 1, okay? Then remember Sn, well, that is a plus ar to the first plus dot 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 ar to the n minus 1. Now if r is just equal to 1, then you get a plus dot 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 plus a, right? You just keep adding a together. And now there are n of them, right? There are n of these a's. Well, that's just n times a. And if a is positive, then as n becomes large, i.e. goes off to infinity, then n times a will go to positive infinity. But if a is negative, n is still getting large and positive, so this would go off to then minus infinity. In either case, you get a divergent sequence of partial sums, which means the infinite series diverges. Okay, so we know that when r is equal to 1, the geometric series is divergent. And I mean, think about it, you're just adding up the same number over and over infinitely many times. That's essentially what you're getting, right? Because r is just 1. All right, but if r is not equal to 1, then let's see what happens here. So first thing, let's recall Sn is a plus ar to the first plus ar squared plus ar to the n minus 1. Okay, Now we're going to do something a little cheeky here. Let's compute r times Sn. Well, that's r times what I just wrote above, a plus ar to the first plus ar squared plus ar to the n minus 1. And let's see what we get. Well, distribute, we get ar plus ar squared plus ar cubed and so forth. And now the very last term I get is r times a times r to the n minus 1, which is actually ar to the n, right? Okay, now let's do something seemingly like you're not supposed to know where this idea came from, but let's just bear with me here, and hopefully we're all going to sort of see the punchline together here. So what we're going to do is we're going to take Sn and subtract from it r times Sn, right? So Sn is this guy right here, this a plus ar to the first plus ar squared, plus ar to the n minus 1. And now we're going to subtract from it what we just found, which is this part right here, right? So ar plus ar squared plus ar cubed plus ar to the n. And now I had to put it in parentheses because I'm subtracting it, right? All right, so let's see what we get. Well, we get an a. No big shock there. But here we have an AR to the first minus an AR to the first, right? Like technically that's a first power there. And so these actually cancel each other. Furthermore, this AR squared minus this AR squared will also cancel. Similarly, there's the next thing we would see here is an AR cubed, which would cancel with that one, right? And even though we're not seeing it, it would technically, there's a cancellation going on there. And now this AR to the n minus 1, well, right before this term, there's an AR to the n minus 1, right? So even though we're not seeing that cancellation, it's also happening. And so the only other part that we're left with is minus AR to the n, right? This guy does not cancel with anything, nor does this leading A here, okay? But now we look over here, and this is still Sn minus R times Sn. What we're going to do is we're going to notice a common factor on both sides. So here there's an Sn common to both terms, and I get 1 minus R. And here there's an A common to both terms, and I get 1 minus R to the n when I factor out the A. And so check this out. Sn is actually A times 1 minus R to the n all over 1 minus R. Right? If I just divide both sides by that 1 minus R. This is kind of a big moment for us because what we just did is instead of like adding up, like we actually found another form for Sn. So instead of doing the long process of adding up n things that look like this, I encourage you to try it out. Pick an A value and pick an R value that's not equal to 1. You'll actually get this shorthand formula for it, right? Instead of having to do the long process of adding up all of these things. So that's actually a really neat result that we came up with here. But here's what it allows us to do. Remember, SNs form a sequence of partial sums. And so if this sequence Sn converges, then the infinite series way up here converges, right? And if this sequence of partial sums Sn diverges, then we say that the infinite sum way up here also diverges. So let's see what happens. If R is strictly between minus 1 and 1, then we know that this R to the n here, the only thing that depends on n on the right-hand side of this equation, will go to 0. Right? We learned that in section 8.1. And so in that case, you would get A times 1 minus 0, which is just A on the top, over 1 minus R. And so for R strictly between minus 1 and 1, either highlight this or put a big old star next to it or something. For R strictly between minus 1 and 1, this is the sum of the infinite series. And so we actually have it right here, right? A over 1 minus r. So you'll have to commit that to memory, a over 1 minus r. Just try to remember that for a geometric series. If r is literally anything else, if it's less than or equal to -1, this was a typo. I didn't have the negative there on a previous one, but if you have the re-uploaded notes, you'll have the negative there. And or if r is bigger than 1, or we know that if r is dead on equal to 1, you get divergent. So geometric series only converge for r strictly between -1 and 1. Notice if you look back in section 8.1, that is very, very marginally different than what geometric sequences do. Remember, geometric sequences converge if r is bigger than -1 but less than or equal to 1, whereas geometric series, you can't have r equal to 1. All right, so let's look back at our example here. Remember where we took n equals 1 to infinity, and we added up a whole bunch of 1 over 2 to the n's? Well, what we want to do is get this to look something like this here, okay? So we're going to use a few common tricks here, the first of which is that 1 to the n is always equal to 1, right? So anytime you see a 1, if it helps you, you can change it to a 1 to the n. And now what that allows me to do is the following. I get 1/2 to the n, right? So 1 over 2 to the n is the same as 1/2 all to the n. Maybe not terribly shocking. But you'll notice that it's not exactly in the right form. I need a number times a ratio to the n minus 1. You'll notice I have to the n power here. That's not good enough. I'm starting with n equals 1, so I need to have an n minus 1 here. So what I'm going to do, and we've done this before just in a different context, I'm going to peel off a factor of 1/2. And now you'll notice that I'm perfectly set up to use this geometric sequence idea. My a value happens to be 1/2, and my r value is also 1/2, right? It doesn't always work that a and r are the same, but in this case it does. Now, you need to ask yourself, is this r value, which is 1/2, less than 1 but bigger than -1? And the answer is, of course, yes. And so this infinite series converges to a over 1 minus r, which is 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is 1. And that's exactly what we guessed it should be in the last video, but now we have proof of it, right? Let's do this problem right here. So let's find this infinite series, 5 minus 10 over 3 plus 20 over 9 minus 40 over 27. It looks to me like we're getting powers of 3 on the bottom. Notice technically there's an over 1 here. So this is like 3 to the 0, 3 to the first, 3 to the second, 3 to the third. So it looks like we're adding up, let's start with n equals 1. On the bottom, we're getting 3 to the n minus 1, I think, because I need to start with 3 to the 0 on the bottom. It's also alternating, right? And I'm starting with a positive, so I know I'm going to have a -1 either to the n or to the n minus 1, and I think because I'm starting with n equals 1, it's going to be an n minus 1. And now on the top, what does it look like I'm getting? Well, I'm getting 5 times a power of 2, right? In this case, it's 5 times 2 to the 0, so 5 times 1. This is 5 times 2 to the first, 5 times 2 to the second, 5 times 2 to the third, right? 5 times 8 is 40. So I think here I'm getting 5 times 2 to the n minus 1 also. And so if I rearrange this, I get sum n equals 1 to infinity. I get a 5 with nothing to do with n. But now everything else has a power n minus 1. So I can combine them into a single parentheses all to the n minus 1 power. And this is the sum n equals 1 to infinity, 5 times minus 2 over 3, all to the n minus 1. And you'll notice this is exactly in the right form, right? It's a number times something raised to the n minus 1 power, where my series starts at 1. My a value is 5, and my r value is minus 2/3. And because minus 2/3 is less than 1 but bigger than -1, this converges And so it's a over 1 minus r. And so that's 5 over, let's see, that's 1 plus 2/3, which is 5/3. And flip and multiply. And so my answer is 3. And so this seemingly weird series here where I'm adding and subtracting these kind of obscure numbers, as long as you can find a form for it and make it look like a geometric series, then if that common ratio r is between -1 and 1 strictly, you know exactly what to do, a over 1 minus r. And so somehow this actually works out to be 3, even though there's no way to tell that just from looking at it. We kind of had to get in with the details. Okay, in the next video we'll do some more, like you can see, converting infinite series into geometric series.